Okay, so just for those of you who just walked in, the TA is going to have special office hours right after this class in this building, 4 to 5, third floor, conference room 322. Okay, so if you have any last minute questions about the lab, please stop by. Okay. I put down a note here on the whiteboard. I'm announcing this in every class. I guess you probably know this by now. Monday is not Monday, Tuesday is exam day. So there is no class on that day. The an evening exam at 7 p.m. in the computer science building, room 142. Okay. Closed book, closed notes, 90 minutes. Okay, now I have actually finished setting the exam, so I will at the end of the class say a little bit what strategy might work best if you want to start reviewing material. Okay, somewhat of a study guide that I'm going to put up, but I'll tell you a little bit about that. Okay, but let's continue our discussion on virtualization. We'll wrap that up, and then we'll talk a little bit about exam prep and whatnot. Right. So last time we were talking about virtualization, and I introduced two types of virtualization: hardware virtualization using type 1 and type 2 hypervisors. Okay. So that allowed you to emulate a processor interface using the native processor interface. Okay. So all of that, so that's virtualization at the hardware level. Today we are going to talk about virtualization at an OS level. This is called OS level virtualization. So you are going to take the system call interface exported by the OS and use the virtualization layer to expose another abstraction, another interface. Okay. That is by and large the picture you want to keep in mind. There is essentially a figure here that shows what OS virtualization does. So if you heard the term container or Docker, okay, all of these things are actually OS level virtualization, unlike VirtualBox and VMware and Parallels and KVM. Those are all hardware virtualization platforms. So okay, Docker and containers do OS level virtualization. Okay, so the picture you want to keep in mind is one that is shown here. Okay, we'll ignore the one on the right, but look at the one on the left. So you have your machine, you boot a normal OS on that machine, okay, and then you might have some processes, you encapsulate them inside what is called a container that provides you OS level virtualization. Okay, so what does this do for us? It provides us isolation. So anything that is running inside the container, you can limit what it sees outside the container. Okay, so for example, you can say you cannot see any processes that are not running inside this container. Even though there are processes running outside, the container does not see them, or you can limit what files are seen and so on. Okay. You can also allocate resources to containers, as we will see. Okay, so this is a mechanism that is going to be a lot more lightweight, okay, than regular type 1 and type 2 virtualization. And to understand why, here is a picture. Okay, I do not know if anyone can see this in the back, but let me explain what these three things are. Okay, so this is type 1 hypervisor. I showed you this picture last time. The one in the middle is type 2 hypervisor. We saw that picture as well. And the third one is OS virtualization. Okay. So what should be clear from this picture is OS virtualization is a very lightweight virtualization technology as compared to both type 1 and type 2, which are more heavyweight. Okay. Why is that? Okay. So the first thing you have to realize is in both type 1 and type 2, inside the virtual machine, you are going to run a whole operating system, okay, whether it's Windows or Linux or whatever it is. Okay. And then you run processes on top of that OS. Okay. In OS virtualization, you will see that you only have one OS, which is the OS that booted on this machine. There is no second OS that is running inside the virtual machine or inside the container, or only processes running. Okay. So that is going to make it faster, because you do not have to boot up a second OS. You do not have to boot a OS inside every VM. Okay. There is only one OS, that is the native OS. Okay. So it is going to be faster and also going to be lot more lightweight, because you have only one OS again. Okay. You do not have here, the more the software layers, the more overhead you are going to incur. So you have the host OS, the hypervisor, a guest OS, that is already 3 layers, okay, that you have to deal with. Okay. So all of that becomes one layer, which is just the native OS. Okay. So think of OS virtualization as a much more lightweight platform. Okay, it's much faster to start a container, because You don't need to put an OS, you just start it and put a process in it, just start the process. Okay, that is all you really need to do. Okay. So, that is the good part. Okay. Now, looking at this picture, what do you think might be some downsides to OS virtualization? Okay, the upside is more efficient, more lightweight, less software overhead and so on. Yes.
Can I actually test things out on a real operating system?
You can test things out. I'm talking. Oh, you cannot. Okay. Yes. So you cannot run multiple OSs. That's a given. So of course that's going to be anything you could do by running multiple OSs. You cannot do. Okay. Yes.
I think less redundancy with if the OS crashes, all of these are gone. But hypervisor, I mean, same with the hypervisor, but
Right.
less likely.
Okay. So there is less OS level isolation in this case, right. So if you have a bug in the OS and you either inadvertently or maliciously trigger that bug, okay, in OS virtualization everything goes down because the OS goes down. Okay. All other containers will fail as well. But in both type 1 and type 2 virtualization, if you exploit a bug in the guest operating system, only that VM is going to go down. Okay. Other VMs have independent OSs, and in at least type 2, there is something that is running underneath, which is the host OS. So, neither of those are impacted. Okay. So, there is so the right way to say this is there is more isolation that is provided by type 1 and type 2 hypervisors than you have in OS virtualization. Okay. So, this by isolation I mean by exploiting OS bugs is more safety than isolation, but there is also some impact on isolation. Is that clear? Okay. Okay. So, now let us look at what does this mean and how does it work. So, essentially it is a very lightweight mechanism for you to isolate processes that are running on your machine, okay, and then provide some resource allocation to a group of processes. That is essentially what it is, and I am going to draw a picture here using these markers which do not seem to work very well. Let me show you what this means. Okay. So, let us assume that you have a machine, okay. It runs, it is running some processes which are shown in circles here. Okay. This has a disk, okay, which I cannot seem to hold on. Okay, and the disk has some files. Okay, and then there you have an OS. Now, typically if you did not use any containers or any virtualization, all of these processes can see other processes. The presence of processes is visible. All processes see the file system. So long as your permissions, you can access all files and all of that is true. Okay. Now, what containers allow you to do is to actually draw boundaries. So, you can say, can draw a group saying these processes, whatever are drawn in red. Okay, so here I will draw it in blue. Okay. So, I drew this boundary which is basically an encapsulation of processes and an encapsulation of files, and you can say that is a container. So, what that means is processes that are inside these boxes cannot see anything outside that box. That means these processes, only these two processes can see each other, they cannot see these other two processes. These processes can only see those files and nothing else. Okay, so, you can limit what files you see, you can limit what processes you see. Furthermore, you can say this container gets 2 GB of memory, okay. It gets so much CPU. So, you cannot actually get, even though the machine might have more memory available, more processing capacity available, you are going to limit what these processes actually get. Okay. So, by performing this isolation of processes, isolation of files and doing resource allocation, we get this abstraction which is called a container. That is really all there is to it. Okay, there is no hypervisor that is running, that is doing anything special. This is just a way to provide a better way to isolate and allocate resources to processes. Okay. Any questions on this? Okay. So, the way we are going to do this in Linux is through some mechanism. So, there is something called namespaces we are going to see very soon, that is going to give us this process level isolation. So, you can say that these processes in this namespace cannot see anything else. Okay. We are going to look at something called cgroups. Okay, that is a Linux level mechanisms, not specific to virtualization or containers, but C groups will allow us to say once you draw this boundary, you can say what resources it should get, how much RAM it should get, how much CPU you get. So, you can then do resource allocation. Okay. So, the first one is isolation, the second one is allocation, and then you will also look at things like chroot, which allows you to say only see these files or this sub directory tree in the on my disk and nothing else. Okay. So, the combination of these three things allows us to actually implement Linux containers, and then we will see Docker actually runs using Linux container on top. Okay, so, let us go through these one at a time. Okay. So, let us start with namespaces. Okay. So, what are namespaces? Namespaces is an abstraction that allows you to restrict what a process can see, which is what I already mentioned. So, you essentially get the illusion that you are the only process in the system. Okay. So, let us try to think from an OS perspective, what does that mean? Okay. What does it mean that this process cannot see another process? Any thoughts on what? Yes. Okay. So, you cannot send, if you are a process in a container, if you try to send a process message to a process outside the container, it is not going to work. Okay. But more fundamentally what is happening is, if you actually do something like PS, which allows you to see all the processes that are running, you will only see that subset. Even though if you run PS outside, you see all the processes in the system, from inside you only see those processes. So, the presence of other processes is not even known to you. Okay. Hence, you cannot even send a message to such a process. Okay, because it will just look like you are sending a process to a message to a non-existent process. Okay. So, you will not see process IDs, you cannot send messages, you cannot do any signaling. So, all of that is limited once you actually put a process in a namespace. Okay. You can have as many namespaces as you want. That dense looking picture at the bottom shows you 3 that you created, a blue, green and red, and you put processes in each of see anything outside that namespace. Okay. Okay. So, you can also, yes, your question. Okay. So, question is, does it look like you are using 100% of the CPU itself? At this point, we have not limited what resources are being used by this namespace. We have just limited what you can see, not how much you can use. We will come to how much you can use when we do the next slide. Okay. So, that is going to be C groups. This is just saying I cannot see. So, if you other processes, but it does not limit you from using resources. Right. You can use as much, unless you are limited, that you can use as much memory as you want, you can use as much CPU as you want. There is no limit at this point. Only thing is, you do not actually see the presence of other processes, that is all there is to it. Okay. Now, you can not only limit the presence of other processes, you can do other things like you can also have users that are assigned to namespaces. Okay. So, just as you have, let us say, a set of login names and passwords on your machine, you can say these users can only be seen in these namespaces. So, inside that namespace, some other users who exist on the system will be invalid, because you cannot actually see them. Okay. So, the presence of users can be limited. You can also limit which network interface cards are seen. Okay. So, if you have multiple interface cards, you can say this namespace or this container can only use this card. So, for example, you might have an Ethernet card and a Wi-Fi NIC. Okay. So, a wireless and a wired NIC, you can say this container can only use my Wi-Fi interface. So, in that case, if it tries to send any data on the wired interface, it will not be able to, it will not even see it. Okay. So, you can limit the network interfaces, limit user IDs, limit process IDs and so on. Okay. So, also you can actually limit mount points and so on, saying you can only see certain volumes. Okay. So, that is the concept of a namespace. Okay. The next is the question that was asked, saying now that I created a namespace, which is a grouping of processes that basically only see each other, but nothing outside that grouping, and some files and users. Next is, how do you limit what resources this namespace can be used? That is done through the C group abstraction. C group is essentially a command, okay, that in fact you will do a lab where you will change all of these things. You will create a namespace, you use C groups to allocate and memory to that namespace. So, you will understand how actually a container is made, okay, in a subsequent lab that is going to come after spring break. So C groups allow you to do resource isolation. What does that mean? You can set upper bounds on how much resources can be used, an upper bound on how much CPU can be used, an upper bound on how much memory can be used, okay, an upper bound on how much disk bandwidth can be used, and so on and so forth. Okay, so you can set these upper limits, and then the processes inside that namespace are only going to be limited to using those many resources and more. Okay. So, how do you do this? I am going to tell you about one technique to do this, which is called weighted proportional share scheduling, but to some degree you should know how to actually do some of these, because you built a lottery scheduler. Okay. A lottery scheduler is a way to allocate resources. Okay. It does not actually put a hard upper bound, but it is going to give you an upper bound. So, if you have two namespaces or two containers, you can give them different number of lottery tickets, okay, and say that is how I am going to control the amount of CPU you get. So, if you give 1:1 to two of them, they are going to get 50% of the CPU. If you give 1:2, the first one gets 33%, the second one gets 66%. Okay, and so on and so forth. So, that is one way you already know how to do this. Okay. What I am going to talk about is a different type of a CPU scheduler that allows you to do exactly that in a deterministic fashion, which we have not encountered so far. But so, there is a deterministic version of lottery scheduler which also allows you to do the same things. Okay. And so, that is called fair share or weighted fair share scheduler. So, I am going to talk about that in just a moment, but you can also do other things. You can also say I map namespaces or containers to cores. I say that if I have 4 cores, then 1 core is given to this container and it will only run at 1 core, even though other cores may not be used by anything else. So, you can do all of these things using C groups. Okay, so, let us talk a little bit about proportional share scheduling. Okay, this is also named fair share scheduling in the literature. It is a deterministic version of a lottery scheduler. Okay. How does this work? Essentially, every resource that you want to allocate, you can essentially assign a weight to let space or a process. Okay. So, you can, so let us say process 1 gets weight W1, process 2 gets W2, process 3 gets W3, and so on. Okay. And then the scheduler is deterministically going to schedule a process, so that the resource is allocated in that proportion. Okay. And exactly the same concept as lottery tickets. The weights represent same as lottery tickets. Okay. So, you can give it a weight. So, if the weight is 1:1, you get 50%. Okay. In this case, it is going to schedule deterministically. What does that mean? So, when you run your scheduling the schedule function, okay, in lottery scheduler, you do a random number generator that allows you to say which process won the lottery and that gets to run next. Here, you are going to explicitly track what process got scheduled. So, if you do 1:1, you are going to alternate the quantum. Right. So, this one is going to run and then that one is going to run. So, you are going to track. If you do 1:2, every time this runs, this is going to get 2 quant. So, you are going to schedule that twice explicitly and then schedule the other one. So, you are essentially doing a more deterministic version of that randomized scheduler. Okay. I leave out the technical detail. There is an equation that allows you to track how many quantum each process has received and is it in proportion the weight. That is what is used by the scheduling function instead of using a random lottery. Okay. But essentially that is what it is doing. Okay. So, this is going to be used in Linux. So, as you can see, the lottery schedulers, deterministic versions of like fair share schedulers, they are used in virtualization frameworks quite a bit. Okay. You can also use them in routers and on your network interface cards, essentially to partition your bandwidth. Okay. You can say for every 1 packet you send, this container gets to send 2 packets by basically just by assigning either lottery tickets or weights. Okay. So, you can say do that and that will allow you to give more network bandwidth to one container over the other. Okay. So, all of that is essentially done using this notion of proportional share scheduling. Okay. So, there are many variants of this. This is not one technique. There are literally dozens of variants of proportional share schedulers and many research papers that have been written, but by and large they all do this one thing, okay, which allow you to give a weight to either a process or a process group, which is essentially a container, and allocate resources in proportion to the weight. And in doing so, you essentially also give bounds on what is the maximum amount of resource that you can use. Okay. Now, there are some issues you want to keep in mind. Some variants of these are actually going to cause starvation. Okay. So, for example, what might happen is you have given two processes weights 1:1. Okay. Let me just write this down, or let us just call it 1:10. Okay. Now, if both processes are active, for every 1 quantum received by the first process, the second process gets 10 quantum. Okay. Typically, the way the scheduler tracks this is keeps a counter. Okay. The counter is going to tick every time you schedule it, right. So, basically you say if this counter is 5, this has to be 50, because you have to have 10 times as many, because that says I used 5 quantums, then this one should have used 50 quantum. Okay. Now, let us suppose that the process at weight 10 or lottery ticket 10 starts doing IO, it becomes it is blocked, okay, is no longer active. So, it is going to go off and just wait. Okay. In the meantime, the first process is active. So, it is going to keep getting scheduled, because there is no other process to run, right. So, its counter value keeps growing, because it gets scheduled more and more. Okay. Now, after it gets runs for a while, let us say this process actually becomes active again, its IO is done. Okay. Its counter has not increased since it was doing IO, it is still stuck at an old value. Okay. In the meantime, this process has executed many quanta and its counter has increased significantly. Okay. Now, if the process CPU scheduler looks at this and say this should have gotten 10 times as much as this other process, you will essentially starve this process for a while and keep running the second process. Okay. For no fault of the first process, all it was just executing on the CPU by doing IO, this process seems to be getting an unfair share of the processor. Right. That is what that last point is saying that you can actually, if you just do this in some trivial way, you are going to get all kinds of problems. So, you have to deal with all of this, and that is why you have many variants of the schedule. The early ones suffered from this problem. So, you essentially, if you got blocked and became active again for long periods of time for everyone else. Okay, yes, question.
The share-based scheduling and the credit-based are different variants of this?
Yes. So, there are many variants of them. So, I think if you just do allocate credits, that you have this problem, right. So, but what you have to do is account for when you block, you do not want your counter to reflect an old value, you got to still take it as if it is executing. So, there are ways you can get around it. So, you do not accumulate credits because you are not running and then use them all at once. Okay. Is this clear? Okay. So, you will see that actually Linux has support for multiple of these, and this is just a patch that was made back in 2016, which said we put in a fair scheduler that tries to use weights and tries to get around some of this starvation problem. They call it a completely fair scheduler, okay, but haven't proved that it is completely fair. They just called it completely fair. So, whether it is completely fair or not is a different matter, but it is a variant of a proportional share scheduler. Okay. So, it is something that you can actually use. You do not have to use this for scheduling containers. You can actually change the CPU scheduler, the default scheduler from MLFQ to credit based, and then that is what Linux will use to schedule all processes. Just as you made your Minix run lottery scheduler, which became the CPU scheduler that is default, you can do the same thing in Linux as well, okay, because there is support internally for many different schedulers. Okay. So, this just puts it all together as far as containers is concerned. So, there are 2 or 3 concepts. One is you are going to have the notion of a namespace to isolate, you are going to have the notion of a C group to allocate, okay, and then you basically have some other tools that we are going to see, which are user space tool, that allow you to use this in an easy fashion. Okay. So, if you take all of these techniques and put it together, you are going to get Linux containers or Docker and things of that sort. Okay. So, what does Docker add to this? Okay. So, Docker is a software layer or a set of user space tools that essentially uses Linux containers underneath. Okay. So, what it has done is added tools that make it very easy to create packages that you can download and run as containers on your machine. Okay. So, it is easy to create these packages, a Git repository to have version packages, you can push packages to developers, you can download things from a Docker repository, is essentially a Git repo, and then run it without having to do much other than download and start running the container. Okay. So, it provides many software engineering benefits that have very little to do with containers at all. Okay. First thing it does is it allows you to package complex applications, okay, so that you can just download, you don't have to compile them, configure them and then run them. Okay. The old way is, if you want to get a new application to run on your machine, you got to download the source code, you got to compile the source code, then you have to read the documentation because there will be some configuration file that you got to go and change, and then you run. Okay. You don't have to compile, you can go to a binary repository, the binary, but you still have to configure. Okay. And configuration non-trivial. As the software packages get more complicated, there are ever more configuration details you got to worry about, and it takes a long time for you to actually really get anything complex to run. Okay. Docker simplifies this because somebody has already made a package made as a Docker image, okay, where the binaries are installed, there is some good configuration already done. So, you just download and you start the container, your process is up and running. So, a lot of complex software is now distributed as containers. So, you do not actually have to download something complicated, there are databases or key value stores or web services and things of that sort, where you might have multiple software components. It is much easier to actually deploy them as containers. Okay. And clearly that really is more soft, there is a way of packaging and distributing your software without having to put too much burden on the end developer. This really has nothing to do with containers, but containers made it very easy because you can also run that package in isolation. Okay. So, what that also allows you to do is, if the libraries that package needs are different from the ones on the native machine, you can actually ship those with your package. You do not have all kinds of other dependency, because one of the other problems when you try to install a piece of software is it depends on 10 other things. So, then you got to first get all of those 10 things and install them, and then you can get your application to run. So, all of that dependency goes away because you can package everything you want and send it in as one package. Okay. So, it is portable, it will run across OS platforms. So, once you have a Docker image, okay, all the dependencies are in there. So, it will run on different versions of OSs, even though the native OS might have different libraries, different version, it will still run. In that sense, it basically going back to the definition of virtualization, I said you are essentially emulating the interface where the package was designed. You do not really have to worry about what is the OS interface, what libraries are installed and so on. Okay. So, you are going to have portability, you are going to get fast deployment, it is easy to build and so on. You will build a Docker image as part of your lab, and they are self-contained, they do not have any dependencies. Okay. Here is the picture. Okay. So, this same picture I showed you earlier, that is type 1. Yeah. So, I think that is containers, there is no type 2 here. So, those are the containers, and then that green thing is essentially what you added to the container, which is a set of user space tools really. Okay. Docker has not changed anything, the virtualization part, that is a plain Linux container. What you did was added a way by which you can create and distribute containers easily, right? Repositories and software development tools. Any questions on this? Okay. So, here are some things you want to think about. Okay. So, I said Docker is a Linux container technology. I do not know how many of you use Docker, but if you have, you do know that it actually runs on multiple platforms. So, you can get Docker for Mac, Docker for Windows, of course, Docker runs on Linux. So, we have to ask, why does that, how does that work? Docker is actually a Linux container or Linux virtualization technology. Do you understand the question? Okay. So, it is basically, if you are not running on native Linux, the way Docker works, Docker actually runs on Linux, it can't run on anything else. Okay. So, if you are running Docker on Mac or Docker on Windows, there has to be Linux somewhere in the picture, even though you do not see it. Okay. So, when you are installing Docker, it will create a very lightweight Linux VM which is running under the hoods. Okay. And all of your Docker images are actually running on that lightweight VM, even though you no longer see that VM. It is not actually running on Windows, it just looks like it is running on Windows. Okay. So, keep in mind that Docker for Mac and Docker for Windows is different from anything I said here, except that when you do run it on a different platform, you actually have a Linux VM and proper VM, which is like a virtual box VM that's running in the background, which you do not see really. Okay. So, all your containers are running on that Linux kernel, not on your native machine. Okay. But if you are running Docker natively on Linux, you do not have that extra overhead. Okay. So, on other platforms, it essentially becomes containers inside a type 2 VM, because you have a Linux VM that is running as a type 2 VM in the background. They did a good job of hiding it. They do not make you install Linux and then install Docker, but that is what is happening. All right. So, that I did want to mention that. But as a result of what they have done, it looks like you can make a Docker image and you can run it on Windows, Mac, Linux, it just runs. Okay, because they essentially made Linux on all of other platforms as well under the hood. Okay, but that gives you, looks like you have cross platform compatibility. You can essentially take a Docker image that is built and then you can run it on a Mac if you are Docker on Mac running, or run it on Windows and so on. So, from a developer standpoint, that is very good, because you do not care what your development machine is, it just runs. Okay, and you the same application, and it doesn't, you do not have to create 3 types, 3 binaries, one that runs on Windows, one that runs on Linux, and one that runs on a Mac. The same thing runs on all platforms. Okay. No different from Java, which is also cross platform, but this is more in terms of allowing you to encapsulate entire applications. Okay. The other nice thing about Docker is it actually makes very efficient use of the underlying file system by using a special system called a union file system, which we have not seen so far. Okay. So, what does union file system do? Okay, so, let us say you have some file system on your machine. So, there is a root directory, there is user, there is local, there is home, there is lib, and so on. Okay. That is your file system tree. Okay. Now, when you have a Docker image, it has its own file system that it has been built to. Okay. Now, if you did not do anything special, the disk of this container is going to be as large as a normal file system, because it basically says everything that this thing needs is packaged with it, which means that all the file systems, the file libraries are packaged with it. Okay. So, if you would actually install this without doing anything special, this image is going to be large, because it has to have a copy of all the file. Okay, and some of those files may be duplicate of this file, because it may be the same file system. Okay, when you do a union file system, what you do is you take this file system and this file system, you literally do a set union, which means that if the files are the same, you do not have 2 copies, you have only 1 copy. Okay. So, only the extra diff is added on to that file system. Okay. That is a union file system. So, it makes use of files that are actually stored, because you do not have 2 copies. You essentially take a union of what is there earlier and what you have added on to it. So, everything that is here is still visible, and all the new stuff is just like adding a delta, just the extra part is added to your file system, and it just looks like one big file system. You do not see that there are 2 file systems, one layered on top of the other. Okay. That is called a union file system. Okay. Now, it makes good use of storage space, but there are some subtleties to deal with. Okay. So, let us say you have a file user, yes. Okay, there is a file user foo, okay, which is visible both outside the container and inside the container. Okay. Now, let us say there is application here, okay, that modifies this file user foo. Okay. Based on our understanding, those changes should be visible inside the container because you made the modification to anything else outside the container. Okay. That is what we said, you are isolating whatever is inside, you can make changes and it is not visible outside to anything else. But if you are, because of the union file system, if you go and modify this file, it is going to become visible to every other process in the system, which violates our assumption of isolation. Okay. Because if you had kept two separate copies, this would not be an issue. You have your own private copy and this is the root file system. You make a file change to your private copy, that is fine, nothing else is going to see those changes. But we said we are going to be smart and we are going to make a union file system to save storage space. Okay. So, now many files are common. So, if you make a change, it becomes visible outside. So, you got to deal with this issue. Okay. Is that clear what I said? Yes.
2 copies?
You make 2 copies. So, of course, you have to make 2 copies, but this technique has a name. Okay. This is called copy on write. It is called cow. Important technique. It is not just used here. It is used in lots of different scenarios in operating systems, distributed systems, and so on. So, this is called very bad markers today. Okay. So, this is called copy on write. Okay. Copy on write essentially is a form of doing what is called lazy copy. So, you basically share 2 entities share one file, and even though they should have 2 copies of it, but only when you make a change do you actually make a copy and have them diverge. Okay. So, in this case, if you write to user foo, there will be 2 copies of foo actually stored, one that is specific to that container and one that is still native to the file system. Okay. So, you are only making a copy as you need to, because at that point you got to spend that extra storage space because you cannot just have one copy anymore. Okay. So, this is called copy on write. Okay. So, you essentially have a union file system that is a copy on write or a cow file system. So, lots of things are going to essentially save a lot of space for you, only things that are going to diverge from the native file system because you started writing to it will have a second copy. Okay. And the file system has to track everything. Okay. This is exactly like you made a fork of a Git repository. Okay. So, then you can start diverging from the main trunk and you will have your own changes which no one else can see in the main tree. Yes.
If a container is isolated, should it be able to read the underlying OSS files?
Okay. That is a good question. Question is, the container is isolated, should it be able to use the or see the underlying OSS file. Okay. So, typically when you create the container, you are going to allocate a file system to it. Okay. Those are the files it should see. All right. Now, as I said, you can, the way you typically do this is you could say this container has no restrictions, it can see everything that the underlying file system has. So, all the files are visible, or you can say this container is limited to the user directory. Okay. So, inside here you will only see /user, you will not see /lib /local those are not visible. Okay. So, that is the basically the namespace abstraction we were talking about. So, you can limit those what you can see and what you cannot see. Okay. That is what containers allows us to do. What we are talking about here is a different concept. Okay. We said we download a Docker image that somebody else built. Okay. When they built it, they said these are all the files that you should see. You should see user, you should see local and all of the libraries and so on. So, when you download this, one way to do this, you should take all of those files and you download them and you keep them in your file system. But he said that is wasteful. So, what you will do is something smarter. You will actually look at which of those files are similar to what is already there and you will share them between the 2, because this is supposed to see those files. So, you will not make 2 copies. Okay. So, that is slightly different from saying what you cannot see. This is both you are allowed to see this and the OS is allowed to see this, but you only keep 1 copy instead of 2 distinct copies. Yes, question. Where is the copy saved? It is actually stored on the native file system.
So if you have external storage, how do you
Yes, if you have external storage, how do you see it? That is why it is called a union file system. Okay. As I said, it looks exactly like a Git repository. If you understand how Git works, okay, you have a main trunk. Okay. By default, all developers see the main trunk. Okay. But you can create a fork of your repo and then start following a fork, and if you are following the fork, you only see the files in the fork. So if you are in the main trunk, you don't see the fork. Okay. Exactly the same thing happens here. Okay. You have a file system tree, and now once you make a copy and write, there are two versions of the file system. Okay, there is a version that actually has these changes that was made here, and there is a version of the file system that does not have the changes. Everything outside sees this part, this view of the file system. Here you see this view of the file system. Basically, all the files are stored as a union, but what you see is a view of that. You don't see everything. You only see what you are supposed to see, even though their disk stores everything.
My question is like when you so when you have when you unmount it as a volume
Yes.
in the OS, the Docker will like the process inside the Docker will still looking for the files in the external storage, but it cannot find like what will
Right. So if you are asking if I unmount some volume here and the container is using it, it will no longer see those files. Is that your question? So typically, if a process is using files in a volume you will not be allowed to unmount it. It will say that the volume is busy, and that's nothing to do with container. Even if there's a process as a file open, as a safety feature, the OS will say unless you force unmount it, you will not be allowed to unmount it. So that problem is not going to be there.
so Docker will basically log every single drive that's connected to the OS when it's started.
So it's not every single drive as much as what root file system it's supposed to see. If you have mounted some other volume that's independent, you are not even supposed to see it here. Right? If you have NFS mounts or Samba mounts, you don't actually see them inside the container. You can unmount them without any problem. It is basically the root file system that we are talking about. Okay? Yes.
This UFS is only running on Docker. It's not running on the OS, which is on top, and that file system is completely independent.
Right. So Union FS is something that Docker will add. I mean, you need a little bit of kernel support for it, but so the disk is actually going to store multiple copies of the file and all of that, but only some things are visible here and some things are visible inside the file.
So I could run NTFS or whatever on my Linux.
Yes. So you can run other file systems. It's independent of this. Yes. Anything else? Yes.
So if I make a new file inside Docker, though, it doesn't make a copy or anything, that's just a single file inside this AUFS.
Yes. So if you make a new file which did not exist at all, you will basically have that file here. It's technically stored here somewhere in this file tree. It won't be visible to outside entities, but yeah, that's going to be local to you. Right. This is just an efficient way of using all your storage space. I mean, the easy way would have been you have your private copy. There's a root file system. You make your changes. They are not seen outside. These changes here are not seen inside. Everything is done. Right. But that's going to waste a lot of storage space. So they said, let's make this efficient. So let's make a union of everything. But each entity sees a view. You don't actually see everything. Okay. Anything else here? Okay. So I'm going to say a little bit about where virtualization is used today. Okay. So we started with saying this 1970s technology last time, right? But now it's even more popular than what it was designed for. It was designed for ensuring that you buy a new machine, you don't have to port all your applications by rewriting code, they just run. Okay. So that was the original use case, but now the use cases have changed quite a bit. So you run them in data centers, where data center is essentially machine with a room with racks of servers. Okay. This room used to be a data center. That's why it has this funny floor. Right, because it is all hollow floor with wiring underneath. But be that as it may, data centers now you have large servers. Okay, you might actually not want to allocate an entire big server to applications. So you construct virtual servers by having VMs and then run applications inside VM. So that's where a lot of virtualization is used. All data centers are now virtualized. They essentially are virtualized typically either using type 1 hypervisor, or the more popular way is to use containers and use framework like Kubernetes, which we will get to. Okay, we'll come to Kubernetes, which is a container scheduling framework. Okay. So, a data center is big use case. Another use case, cloud computing. Right. So, in a cloud platform, you essentially go and say I need a machine, and the cloud provider, let's say it's Amazon or Azure or Google compute engine, say here's a machine, you can now SSH into it and use it. Okay. Typically, they are not giving you a real bare metal machine, because if you are root, because you are root on your machine. Okay. If you are root, you can do whatever you want, then they cannot take the machine, they lose control over the machine. So, what they do is they essentially run a type 1 hypervisor, and what they are giving you is essentially a VM, not a real physical machine. Okay. So, that's another use case. So, practically every cloud provider essentially use virtualization for reasons of retaining control over their physical machines. So, the customer machine dies or goes haywire, you still need control. Okay. So, that's a second use case. Third use case, of course, desktop computing. Okay. You can use this to do code development, you can use this to run other OSs on your machine for whatever reason. Okay. The code development is big use case actually. So, there are all VMs that are essentially have a build environment, where you can write your code and then you build in a VM, and then you can test it in yet another VM, you can have test environments in other VMs and so on. Okay. So, software development processes use VMs quite a bit as well, okay, in addition to developers actually using them on their machines for developing code and so on. Okay. Here is yet another, yes, your question.
There are certain servers called uncheck servers where independent server blades are combined into a single server, and then virtualization is done on top of that to divide into multiple pieces. So instead of combining them and splitting them, why don't they put an hypervisor and dedicate one to one person?
Are you asking about blades? What is the question you are asking?
Usually blades are combined into a single moonshot, and then virtualization is added, and then it's split again.
Yes.
So that one server goes to each person. So instead of that, if just put hypervisor on each blade and then provide that to
Yes. So, there are many ways you can actually allocate resources, right. So, the scenario you are talking about is a blade server, which is made as a one logical pool of resources, and then you make VMs on top of that, right. Lot of clusters look exactly like that. When we come to Kubernetes, you will see that is what it does. It takes a set of machines and makes it look like a large pool, and you say give me a VM, it will basically make a VM and give it to you. So, you do not actually control, you do not say give me a VM on that machine. Okay. What you are saying essentially says I will expose the presence of machines, and I will say I want a virtual machine on that physical blade or on that physical server. When you have lots of machines, physical machines, that is, you do not, if you need a VM, you do not care where it goes. So, there are frameworks that abstract it out. The one you are talking about abstracts it, or so do many other cluster managers. So, they manage the placement of which VM goes on which physical machine, and they do not actually let you have to deal with that. Okay. So, it is simplifying your job is why they did it. You could have run a hypervisor on each of the blades if you wanted to. In fact, I think it still does, right. It is just not exposed to you. Other questions? Okay. So, here is yet another use case, which is to do distributed research across universities and so on. It was actually a very early use case. There is a system called PlanetLab. I do not know if anyone has heard of PlanetLab. Okay, some of you are shaking their heads. So, PlanetLab is a distributed infrastructure that allows you to run experiments across the internet. Okay, so, if you are a networking researcher, it is a very valuable platform. Okay, you want to test a new networking protocol, maybe you built a new video streaming protocol, you want to test it over the internet. Okay, the old way was you call up a friend saying, can you give me a guest account on your machine, you run some code there, you run some code here, then you do some experiment over the internet. That does not scale if you want 100 machines in 100 different sites that you want to test. So, what these people did maybe 20 years ago now was they said let each university have a few machines, they are going to contribute to this large infrastructure, and then we will basically run containers on them, they run Linux containers. We can basically automate the creation of accounts and so on. So you can just go to one central node and say, I need 5 machines across 5 sites, and you can say I need one at this university, this university, this university, and so on. And then it will create a container for you on each of those, and then you can log in and do your experiment. Once your experiment is done, you can say terminate it. It looks like a cloud, except that it is highly distributed. Okay. In a cloud also you can do this, but typically you might have only one site or some very small numbers. So these are machines that are spread across literally hundreds of universities across the world. Okay. Allows you to do interesting research experiment. Okay. That is one of the early use cases for Linux container. They did not use type 1 hypervisors. They decided to use LXC, Linux containers, and a software called vServers that ran on top of that, because they wanted more lightweight machines. Okay, and each university had only 2 or 3, so you couldn't run lots of VMs, but you could certainly run lots of containers. Okay, all right. So the last thing I want to talk about is an interesting technique that is possible using virtualization, because we talked about lots of things you can do. Okay, you can take a machine, slice it into smaller virtual servers. You can basically isolate what a process can see and so on. So all of those are good things, but there are certain things you can do with virtualization that you cannot do without. Okay. One of them is what is called virtual machine migration. Okay. So let me explain what this is and why it is needed. Okay. So let's assume that you are running a process on some machine. Okay. Let's say it's a website. Okay. For whatever reason, let's say the number of requests that start coming to this website just grows quite a bit. It may be a small web store, but maybe the product they are selling has become very popular. Load goes up. Okay. Typically, when load goes up, machine gets overloaded, and then it basically stops accepting requests. If you've gone to any overloaded website, you know what I'm saying, right? So it will say server busy, or your machine will just, or your request will just hang. The browser will just sit there waiting for a reply. Okay. So what is the answer to this question? You will say, okay, that machine is, or that website web application is overloaded. Let's put it on a bigger machine. Okay. Give it more cores, give it more memory. So now it has more resources. The normal way you would do this is you would shut that web server down. You will move all the code, you will move all the data to another machine. Then you will start everything up, and hopefully things will be better. Okay, but that means there's a downtime. You basically have to take the application down and move it and so on, okay, which may not be desirable if you are actually running something important. You can't just take it down in the middle of when users are accessing it and so on. Okay. Now, virtual machines allow us to do exactly what I said without actually seeing any downtime at all, okay, through a technique called VM migration. So, you can essentially take a virtual machine on one machine and say just move it to another machine, and this VM migration technique will do it while the application is running. The application won't even know that it has moved from one machine to another. Okay. So this is called VM migration. This kind of stuff you will not see without virtual machines at all. So you might have, in this case, 2 machines. All the markers are dying. So you have 2 machines. So you have a VM here. You can essentially just move it there, different machine, without having to shut anything down. The OS will run, the application will continue to run, everything will look exactly the same. No one will actually know that the machine has moved. Okay. So that's a good technique. We'll see how to actually make it work. Okay. So that is essentially going to migrate the OS running inside the VM and all the processes. Okay. The entire VM is going to move from one physical server to the other. Is that clear what I said? We'll see how to do it. Yes, question?
How about, data is modified in one VM, how do you handle constances?
Yes, we will see how to do that. That's the part why this is tricky. Right. So there are 2 ways to do this. Okay. I'll talk about the simple way, which is called the pre-copy. Then I'll talk about a different way, which is called post-copy. Okay. So here's an approach. So initially, let's not worry about files on disk. Okay. Let's just talk about what is running in RAM. Okay. So what we have the OS, we have some processes that are resident in RAM. We want to move them all to another machine. Okay, we will see how to do files in just a little bit. Let us not worry about file. So, here is what we are going to do. Okay. Let us just number all the pages in your RAM 1 through n. Okay. So, let us say your RAM has n physical pages. Okay. You have to move all of this data over. Right. So, let us just start copying them in sequence. So, we will send page 1 over. So, basically you are going to essentially go here, take page 1, send it there, page 2, send it there, page 3, send it there, and so on. So, you will send all n pages. Okay. So, once you are done with this, you have n pages on the other machine. Okay. But keep in mind that the applications here are continuing to run. They are going to modify pages. Okay. New process will start, processes will terminate, you will allocate things on your heap. So, while you are copying these pages over, some pages will change. Okay. So, those are actually the pages here shown in red. So, that blue is essentially the RAM of a VM that you are copying, but while you are copying, it shows that 2 pages changed, which are shown in red. Okay. So, what is now on the other machine is outdated, because it has some pages that are the same as the first machine, but some pages are newer on the first machine, it does not have. So, what should we do? Copy them again. So, we will do second round. This time we will not send everything, we will only send what has changed. So, what that means is, while you are sending, you also have to track what is changing. Right. So, when you are sending 1 through n, when you are doing this, every time a page is updated, you say this is a dirty page, that is a dirty page. So, in the second round, you are only going to send the changes. Okay. So, in this case, you are going to send those 2 red pages. Same thing is going to happen again. While you are sending them, some other pages may change. Okay. But the important thing is, since in the second round you did not send all of that data over, you only send the changes, the amount of time it took you to send changes is going to be significantly less than the first round. Okay. If we assume that on average x number of pages change every second, since the second round is shorter, the number of pages that change in the second round will be less than in the first round, the number of pages that change in the second and so on. Okay. So, maybe now next time around, maybe only 1 page changed. Okay. So, essentially in every round, we expect that the amount of dirty memory is that has changed while you are sending the previous round is going to keep shrinking. Okay. Eventually, you are going to get to a point where that the changed pages is very small. In our example, in the third round, there is only 1 page that has changed. Okay. Sending 1 page ought to be fast. Okay. So, what we are going to do in this case is, we are actually going to suspend the execution of the first VM. Until now, the VM was just running, it could do whatever, all the OS was running, it was changing pages, but we are going to suspend it temporarily. Okay. And we are going to now send that page over. Okay. At this point, the 2 machines have an exact mirror copy of one another, because the first one now is suspended, it can't change any memory, nothing is running. We just, this hypervisor just stopped scheduling it, that is what suspend means. Okay, hypervisor, let us not schedule that, so the memory will not change, you send that page over. Now, the 2 VMs look exactly identical, everything that is here is on the other machine. Okay. Now, the second hypervisor will just resume execution of that VM. Okay. First hypervisor will just delete the VM, and now the VM has magically appeared on the second machine. Okay. And you will resume execution from exactly the assembly instruction that you left off here, because you just paused it, you copied the last page. Now, that state is identical here. So, if you resume execution of that VM, it should basically behave exactly the same as the first VM. Okay. This is called virtual memory migration. The process I called you is called pre-copy migration. So, it is an iterative copy. Okay. It is copying in rounds, and the hope is every round will have less data than the previous round. Okay. If you are not, every VM will be this well behaved. Okay. Because if you could construct a workload which says every second just go delete all my memory and reallocate all the memory. That VM is not getting migrated anytime soon, because it is just going to keep on sending data, and then you have a lot more data and lot more data. But most processes are better behaved than that. So, hopefully, we will basically iteratively converge to a small set, we pause the VM. So, there is a very tiny downtime where you send that last amount of data over, which is almost imperceptible, it is in the order matter of milliseconds or less. So you can't see it. It almost look like you are just waiting to be scheduled here, and suddenly you got scheduled there. So you don't actually see anything happening. Okay. So everything is running. So what has happened is all the processes, all of their contents, they move over and they start executing on the second VM. And our hope is the second VM, second machine has more resources. So now your VM can be made bigger and things of that sort. Okay, that's the reason we moved it to begin with. Okay. Do you see any issues with this problem, with this process? Yes. Yeah. There's a tiny amount of downtime, but it is imperceptible. Let's say we ignore it. So let's say that we are willing to tolerate, because you can actually not see it. It's too small to be actually visible to anything. Okay, we don't know how to find the new VM. Yes. What does that actually mean? Okay. We should say, what about the networking aspects of this? Okay. That second machine has a different IP address. We just moved everything over. Okay, this machine may have active TCP connections that are tied to an IP address. You just moved it over, and I said everything works. You should say, why would it work? That has a different IP address. All my TCP connections should break. Right? Yes.
You can use tell a gateway to assign the IP address to the new MAC address and send use ARP to tell a gateway that that MAC address now has that.
Yes. What you said partly true. So we will use an ARP, but we have to do it differently. Okay. So the first thing is you got to realize physical machine A and physical machine B have two different IP addresses. If this VM's address was tied to the physical machine's IP address, we are not going to get this to work, because that IP address has changed. Okay. So here is what we will do. Okay. Or here is what helps us. This VM has its own logical network interface card. Last time I told you that the VM actually sees a different Ethernet card from the physical machine. It's a virtualized card. Okay. It has its own IP address. Okay. And that IP address can actually be different from the, it is different from the physical machine's IP address. Okay. For now, let's assume it's a real IP address. We said we can do NAT and give it 192. Let's assume that's not the case. This is actually a real machine that has a real IP address, which is going to be distinct from the IP address of this machine. Okay. So you can now move that VM over. Okay. This machine has its own physical IP address, MAC address, and a physical IP address. That machine has one too. But that doesn't matter for the VM, because what the VM cares about is its IP address, not the IP address of the physical machine it's running on. And its IP address can move with it. That is not tied to this physical machine. It's only tied to your logical Ethernet card, which has moved with you. Okay. The only thing we have to do is, there are switches here that believe that this port is the one that has this IP address. So what you got to do is send what is called an ARP message to your switch, which says that please rediscover this IP address, it may have moved. This is no different from if you actually had a wired connection. Okay, let's say you had a wired Ethernet. If you actually unplug the cable from one port and plug it into another port, you should know that your machine actually works just as fine. Okay, because all that has happened is the IP address just appeared on a different port. The same thing actually happens here. Okay. So the IP address will actually move with you, because the IP address is tied to your VM. Okay, it's not tied to the physical machine. Okay, well, there's another IP address that's tied to the physical machine that's irrelevant to you. Okay. This is why the networking part is also seamless. Okay. None of your connections are actually going to break at all. Okay. If this was a web server and there are browser requests coming to it and you moved it there, now the requests just start arriving there, because the switch just starts sending all the packets there, because it just sees that the machine is now gone to a different port. Okay. So as a result, nothing much has to change at all. Okay. The OS moves, the applications move, the network address moves, the connections just work as is. So everything is actually exactly how you would expect it to be. Okay. This is why it is actually a very nice mechanism, because you can't do this with normal without virtualization. You cannot actually move a process from one machine to the other. It just does not work, because that process, if it has open socket connection, network connection, those are tied to the NIC on that machine, and the other machine has a different IP address. So, this is why fundamentally things break when you try to do process migration. When you do VM migration, you basically have your own NIC and your own IP address which can move with you. This is what actually helps you in this case. Is that clear? Okay. So, that is pre-copy migration. I will talk about the difference. So, you will see that the last step here is you got to send an ARP message to the switch saying, hey, the IP address that was on this port is now different, please rediscover, and then things will be fine. And the switch can take care of that already. Okay. Here is a different approach that does exactly the same thing. It is called post-copy migration. Okay. In pre-copy migration, we had an iterative copy where we tried to copy the RAM of VM1 onto another physical machine, and it took us several rounds to do this. Okay. Even on a very fast LAN, let us say it is a 10 gigabit LAN, this can take tens of seconds. It can take you up to half a minute to move a VM from one machine to the other. Okay. The application, there is no downtime, but it just still takes some time for you to move it. Okay. What if you wanted to do this faster? Okay, this technique allows us to do that, which is called post copy migration. In post copy migration, what you are going to do is what is essentially called lazy copy. Okay. So, you suspend the VM, okay. You will copy a tiny bit of memory over, okay, just maybe a few pages over. Okay. So, now the second VM basically essentially has lots of blank memory and a few pages that you fetch, and you will start executing that VM. Okay. So, let us say it executes an instruction. What is likely to happen? It is going to page fault, because it looks like that page is not in memory. Okay. Except that now this is a network page fault, because all that memory is now sitting on a different physical machine, not sitting on your disk. It is not a virtual memory which is on disk. It looks like virtual memory is sitting in a different VM. So, you will start paging it in. Okay. And you will also have background process which is just going to keep copying lazily, and as there are page faults, you start bringing in. Eventually, you will bring your working set and you will start executing without page faulting, and there is a different process that is going to run in the background that will keep bringing it over, and after some time all the memory is going to be brought in. Okay. The good thing is the first VM has already been suspended, so its memory is not changing anymore. So, we do not have the problem we had in the first case where processes were executing and changing their contents. You already paused it and started executing it here immediately. Okay. So, here the transfer time is very low, but in the first several seconds there are going to be a lot of page faults as you try to page in your working set. Okay. So, that is the downside. Okay. The other case, it takes a while to transfer before, then in both cases there are no visible signs of the transfer from an application standpoint, other than you see some paging activity in the second case. So, there is no real downtime of any sort, okay, but it may actually see a performance slowdown. Okay. So, this is referred to as post copy. So, most of the things you actually see, which is KVM and others, they actually all support live VM migration. You can start a KVM VM and you can say move it. So, if you have two PCs, you can actually move it live, and you will see that it just moves without doing anything to the machine or processes. Okay. And post copy is more of a research paper that was written. Okay. It was implemented, but most commercial systems do not yet use it, because they think the overhead of this page faults is going to be high enough that the application might perceive a slowdown. So, it is better not to show anything to the application that sees a performance hit. Okay. So, those are the two pros and cons, and here is essentially the analysis of how much time it takes to move. You will see in this case that this is pre-copy. You are essentially sending things in rounds, and then in the end you are going to basically move the VM. Here you move it immediately, and there is a large post copy phase where there is both demand paging as well as a background copy process. Okay. In both cases, the total time might be similar, because you are essentially copying large amounts of data, but in one case the switch happens earlier, the other case it happens later. Okay. All right. So, I am going to pause here, but I just want to take 2 minutes to talk about the exam. Okay. I will put up a very brief study guide. There is no sample exam I have to hand out, but I will put a study guide on the course web page. But here is the basic thing. Okay. My expectation is that you should focus mostly on the course slides, okay, course notes. You do not have to go and read the book end to end or anything like that. I am not expecting anything that I have not covered in class is not on the test. Okay. You are only expected to know what I have actually covered in the lectures. Okay. That is the only thing you should focus on. So, your best bet is to actually start with the slides, look at the material, see what you understand, do not understand, and then either go to the notes or if necessary go to the book or anywhere else, Minix documentation, and read upon that. Okay. But if you understand what is on the slides very well, you should be in good shape for the exam. Okay. So, that is my expectation. So, do not go beyond what I have covered here and what is on the slides. Okay. That should be the baseline case of how you prepare for your test. Okay. And then I will put some more instructions on what concepts from each lecture are important and so on. But that should be, so everything I have done till now is on the test, okay, lecture 1 through lecture 13, okay, and including the Linux lecture, and it's all, it's closed book, closed note, but really it shouldn't really take 90 minutes from my thinking to even complete the test. You have 90 minutes, but you shouldn't have to need it. Okay, yes.
What's the structure? Like multiple choice, free response?
Okay, what is the structure? So, no multiple choice. Some short answer questions, like 2 to 3 sentences you should be able to answer, right? And then, so those are more concept testing, saying what is this concept, answer it, right? And there are some slightly longer ones where you have to say, given this concept, how does this work? So, you got to explain the working of. So, that is the kind of question. There are no math problems, there are no multiple choice problems, no programming. You do not have to understand any code, memorize any code. Nobody is going to say, what did this file in Minix have? No, none of that. Okay. So, do not have to worry about any of that. Okay. Just concepts that we covered here. All right. Okay. So, that is it for now. So, next week we will have the test, then we will have one more lecture, then spring break. Okay. Yeah.
I have a question on the performance degradation of migration time.
Yeah.
So, like in general, is dirty page tracking like the